Hi everybody, the purpose of this video is to go over homework 3.3b. So these are the application problems, and these are going to be applied to the future value of an ordinary annuity, and in one case we are also going to be talking about a compound interest problem. So once again, let's go ahead and get to it. First, notice that I have the future value formula here, and I have it rearranged so that you can actually figure out what your periodic payment is. And also recall that an annuity is basically a financial instrument where you make multiple equal periodic payments. So you can almost think about this relative to compound interest. Compound interest is pretty much what we would think one and done. You make one deposit, one withdrawal, or one withdrawal, one deposit. In a future value annuity, you are making periodic payments. So here is our first question, or our first problem. Here we have this company, Acme Annuities, recently offered an annuity that pays 5.4% compounded monthly. And the question is, what equal monthly deposits should be made into the security in order to have $138,000 in 8 years? So we are looking for payment, which means we want to use this equation. Well, what else do we know? Well, we know that the interest is 5.4%. So that means that our annual interest is 5.4%, which can also be written as, well, 5.4 divided by 100, which would give us that R is equal to 0.054. What else do we have? It's compounded monthly. Monthly means that our compounding rate or frequency is going to be 12. And we know that we want to have a future value of $138,000. So FV is going to be $138,000. And also we have that our time is 8 years. So T is equal to 8 years. Now notice that in our formula we have I, which is the interest rate over the payment period, and the total number of payments, which is N, which we need to figure out. We can't use this formula until we know what I and N are. Well, the interest rate over the payment period is equal to the annual interest rate as a decimal divided by the number of payments per year. And that's going to be equal to 0.054 divided by 12. I do not know that off the top of my head, but I have a calculator right here, and that gives me 0.0045. So I is equal to 0.0045. That is how much interest is earned, fraction of interest that is earned every single month. And then N is the total number of payments, which is going to be the number of payments per year, that's M, times the number of years, which is T. Okay, well, M is 12. T happens to be 8. And 12 times 8, pretty sure is 96, is 96. And now we know everything we need to know to figure out what our payment is. So our payment is going to be equal to our first future value, which is going to be 138,000 times I, which is 0.045, 0.0045, divided by I plus 1 plus I, which is going to be 1.0045, raised to the nth power, which is going to be 96, minus 1. That is the equation that we need to compute. And how am I going to do this? Well, I'm basically going to do this straight on. I'm going to do 138,000, 138,000, that's that, times 0.0045 times 0.0045 divided by. Now to do this part, I need to use parentheses. So open parenthesis, 1.0045. I'm going to raise that to the 96th power. I'm going to move out of the exponent, minus 1, close the parenthesis. And that should be my monthly payment. I'm going to have that PMT is equal to 1152.46, and my third decimal is 9. Since my third decimal is 9, I need to round up, and this will give me that my monthly payment, because I'm doing this every month, is going to be equal to $1,152.47. And let's put that into MML and see if I'm right. And there you go. That is our payment. And we can move on to our next question. Now, our next question is a little challenging because there's actually two parts to this problem. Is actually two problems all wrapped up in one. So notice that we have Bob makes his first $700 deposit into an IRA, earning 7.1% compounded annually on his 24th birthday, and his last $700 deposit on his 39th birthday, which means he's made 16 deposits. That happens to be N for us. Now after that, with no additional deposits, the money continues to earn 7.1% compounded annually until Bob retires on his 65th birthday. And the question here is, how much money is in that IRA? Well, notice Bob is making deposits until his 39th birthday, which is 16 deposits. During that time, this account is essentially an annuity because he's making periodic deposits. However, once he stops making the deposit, well, the account is still earning compound interest, but once the payment stops, then we have a compound interest problem. The beginning value for the compound interest phase is going to be the future value at the end of the annuity phase. So it turns out that the value of the value of the account at 65 is going to be equal to the future value of the account when the annuity ends times 1 plus I raised to the n sub 2 power, where n sub 2 is nothing more than the difference between 65 and 39, which is 65 minus 39, or 26 years. So that's what n sub 2 is. But once again, we have two problems. The first problem is the annuity problem. Once we figure out the future value for the annuity problem, we can apply that as the input to the compound interest problem. Okay, so we know that Bob is making $700 payments. So PMT is $700. The account earns 7.1% annual interest. And that is equal to 0.071. It is compounded annually, so that means that M is equal to 1. And the duration of the loan is 16 years, so T is equal to 16. So all we need to do now is figure out what I is and figure out what N is, and we're good to go. Well, I is equal to R divided by M. That's equal to 0.071 divided by 1, which is just simply 0.071. N is M times T. M times T. That's 1 times 16, which is equal to, you guessed it, 16. So now we know everything that we need to know to figure out what the future value of the annuity is. The future value is going to be equal to the payment, which is 700, times 1 plus 0.071. That was just going to be 1.071 raised to the nth power, or 16, minus 1 divided by 0.071. And in our calculator, we will have parenthesis 1.071 exponent 16, get out of the exponent minus 1, close the parenthesis, divided by 0.071. Okay, hit enter. And that is the value of that particular fraction. We want to multiply that by 700. And that will give us a future value of 19,684.976. Since the third decimal place is a 6 greater than 5, we are going to round up, and that means our future value is going to be $19,684.98. And this is the future value of the annuity. Now, this future value is going to become the present value for our compound interest investment once he stops making money. Then the future value of the account when Bob reaches 65 is going to be equal to, well, it's going to be A, and it's going to be equal to P, this is the P, times 1 plus I times N sub 2. Now remember, N sub 2 is going to be the total number of payment periods, and that means that N sub 2 is going to be the number of years between Bob's 39th and 65th birthday. That will be 26 times the number of payments per year, which is just, or the number of compounding payments per year, which is just simply 1, will be equal to 26. So we will have that A is equal to $19,684.98 times 1 plus I, which is still 0.71. That'll be 1 plus 0.71, or 1.071 raised to the 26 power. Okay, and that will give you, well, now what I'm going to need to do is just come over here, highlight that, that's the number, hit enter. Now, times 1.071 hat 26, and now hit enter. And I got $117,128, and that will be 11 cents. So I have that A is equal to $117,128.111, and that, and notice, and no, I don't need to round up, so that means my future value is going to be $117,128.11. And there you go. Okay, moving on. Okay, now here we have the problem how you can afford monthly deposits of $230 into an account that pays 3.9% compounded monthly. How long will it be until you have the $9,800 you need to buy a boat? Okay, and we want to know what that number is in terms of months, which is kind of convenient because we're going to be making monthly payments. So we want to know how many payments do you actually need to make. Well, to solve that problem, we are going to need to use this formula right here. And we'll solve about the other one, but we are looking for N in this particular case because N is going to map to the number of months. Okay, so we can make monthly deposits of $230. That tells me that our payment is going to be $230. The account pays 3.9% interest compounded monthly. So R is equal to 3.9%, which is also going to be equal to 0.033 3.9% divided by 100. We are compounding monthly, so that means that m is equal to 12. And we want to know our future value is going to be $9,800. Okay, and we want to know what n is. Okay, n is equal to the total number of payments. It's also equal, since we're making monthly payments, it's also equal to the total number of months. Okay, so let's get to it. Now, let's fill this information out. We have that our future value is $9,800. That is going to be equal to our payment, which is $230, times 1 plus 0.0. Oh, wait, no, hang on a second. We're not done yet. What else do we need to do? We can't go ahead and do this. Okay, now we need to figure out what I is. Okay, remember, we're trying to find n, but to do that, we need to know what I is. Now, remember, I is going to be our interest rate, R, divided by our payment frequency, which is 12. That is going to give us 0.039 divided by 12. And that will be equal to, let's go ahead and figure that out, 0.039 divided by 12, and that gives me 0.00325. So I is 0.00325. So now we know everything with the exception of n, so we can put in our numbers and see what we need to do to figure out what n is. So our future value is $98,000 or $9,800. That's going to be equal to our present value, which is $230, times 1 plus 0.00325, or 1.00325, raised to the nth power, we don't know what that is, minus 1, and all that is going to be divided by 0.00325. Okay. So we basically want to revise this equation to solve for n. And the first thing that we can do is we can multiply both sides by 0.00325. And we can divide both sides by 230. Doing so, these cancel and these cancel. So all we have left over here is 1.00325 raised to the nth power minus 1. On the left hand side, we are going to have 0.00325 times 9,800 divided by 230. And that is going to give me that monstrosity right there. 0.138478 is equal to that. Now, I can add 1 to both sides. Plus 1, and then I'm going to have 1.138478, and that's going to be equal to 1.00325 to the nth power. Okay, now I can take the common log of both sides. And the power property of the common log tells me that I can write the right-hand side as n times the log of 1.00325. On the left-hand side, I'm just going to simply have the log of 1.138478. Okay, and now I can divide both sides by the common log of 1.00325. Log of 1.00325 over here. I forgot to close that parenthesis. Log of 1.00325. These cancel, and we have what I'm looking for, which is that n is equal to the log of 1.138478 divided by the common log of 1.00325. And this we're going to need our calculator to compute for us. So what we can do, and we can actually take advantage that the more exact number is right here. So what I can do is I can add 1 to that, plus 1. And that gives me the more exact version of this, okay? And now I can do log right here, okay? And then I can highlight that number. There it is. Hit enter. Close the parenthesis. Divided by, once again, log 1.00325. Close the parenthesis. And that is my value for n. I have that n is equal to 39.97. There's going to be a total of 39.97 payments. Of course, we can't have 9/7 of a payment. That's going to be kind of weird. And each payment is every single month, so this is actually 39.97 months. Of course, we cannot, once again, we cannot do 9/7 of a month, but we can do 40 months. So we're going to round this up to the next integer as required right here, and that means that n is going to be equal to 40. So all that just to get 40. And there you go. Okay, for our fourth problem, we're more than halfway there. We want to use the graphical approximation technique or an equation solver to approximate the desired interest rate. And here we have a person makes annual payments of $1,000 into an ordinary annuity. At the end of 5 years, the amount of the annuity is $5,825.80, and we want to know what the annual compounding rate is. Because once again, we are going to be using this equation. However, what are we looking for? Well, we are looking for the interest rate. Basically, we are looking for I. Okay, that's what we need to find. And what are we given? Well, first thing is we are given the annual payment. The annual payment is $1,000. Okay, we're told that they are annual payments. That implies that M is equal to 1, which is good because that makes our life easier. We don't know what R is. That's what we're trying to find. Okay, we do know what T is. That is 5 years. And since we know what T is, we can figure out what N is. N is going to be equal to, 1 M times 5, or just simply 5. N is equal to 5. And now remember, I is equal to R divided by the compounding frequency, which is 1. So in this case, I is equal to R. So when we find I, we find R. So let's go ahead and set up this equation as best we can. Oh wait, we also need to know what A is. What's the future? What's the future value? The future value is $5,825.80. Let's not forget that 80 cents. Okay, now we can set up our equation. Our future value is $5,825. So 5825.80. Okay, that's going to be equal to 1,000 times 1 plus I, that entire quantity raised to the nth, minus 1 divided by I. So that is our equation. And we want to solve this using want to solve this either using a graphical approximation technique or an equation solver. Well, it turns out that your TI-84 has this thing called an equation solver. And you can get to it by clicking on Math and then hitting the up cursor. And there it is. It's called the numeric solver. Once that's highlighted, you can hit enter. Now what you're going to do is you are going to want to put this information right here into E1, and then you are going to want to put this number right here into E2. So E2, E1. So let's go ahead and do that. And when we put this number into E1, instead of using I, we are going to use this button for X. So let's go ahead and do that. What do we have? We are going to have 1,000 times, and we're going to need to use parentheses twice actually, once, twice, 1 plus X for I, close the parenthesis. And what is n? Well, we forgot to put what n is. N actually is equal to 5, so we can put a 5 there. That's what we should have had here. We should have had 5. Okay, get out of the exponent, minus 1. Close the parenthesis. Divided by, well, not I, but X. That's what goes into this one. Now in the next, in E2, we put in 5,825 and 80 cents. Okay, and now notice how the OK is above the graph. Just basically click the graph key. That's for OK. Okay, now they give us a starting value for X. You can use that. It might be better if you actually get the starting value of X being equal to 0, because it's going to be an interest rate as a decimal, so it should be a relatively small number. There you go. And now we can hit graph or solve. And we get a value of X is equal to 0.0765. Okay, well, that basically tells us that, well, X or I, remember we used X for I in this, is going to be equal to 0.076500. We only need to go to 2 decimal places. Okay, well, if that's the case, then as a percent, then we can multiply this by 100 to get our percentage, and that will give us that I is equal to 7.65%. Now remember, I is equal to R, so this is also equal to the annual rate. That's what we want to put in here. 7.65. And there you go. Okay, we only have 2 problems left, and here is the next one. Now here we have a choice of 4 increasing annuities as shown in the table below, and we want to know which annuity is going to reach $10,000 at the earliest. And we have an interactive figure, so chances are we need to use this interactive figure to figure some stuff out. Okay, so let's go ahead and launch it. Okay, it's called Sinking Fund Model, and now it appears. Let's go ahead and move this over here, and let's bring our OneNote, I guess, down here, and let's see if we can just raise this just a little bit. Okay, so here's our OneNote. Okay, and let's check out annuity A. Now notice our investment goal is $100,000, so we want to change this to $100,000. Our annual interest rate is 5%. Good, we have that here. The interest periods per year is 52, so we want to change this to 52. And the payment per period is $400. And we don't need to worry about number of years. We can actually just leave that where it's at. And notice that once we have all this in, 100,000, 552, and 400, we notice that we will reach our investment goal in 4.31 years. So let's make a note that annuity A will reach its goal in 4.31 years. Okay, now let's do the exact same thing for B, C, and D. Okay, so let's go over for this. Come over here. Once again, we have that the annual rate now is 9%. We are making 12 payments per year. We are making $600 per payment. And that tells us that we will reach our goal in 9.04 years. Okay, that actually makes a bit of sense. So for B, we have 9.04 years. Let's take a look at C. Okay, there our interest rate is 10%. We have one payment per year. That's going to be a deal breaker. And we are making $1,200 per payment. Okay, that means it's going to take us 23 years to get to $1,000. So I'm pretty sure C is out. And then finally, there is annuity D. There's no way annuity D can actually be any faster than B, any better than A. But let's just go ahead and do it anyways. We have an annual interest of 1 whopping percent. Well, that's definitely a deal breaker. We have 4 compounding periods per year. We're doing this quarterly. And we're putting in a whopping $94 per pay period. And it's not even close. So D is definitely out. A is 4.3 years. B is 9. The answer is obviously going to be A. There we go. And now we have one question left. For some of us, I thought we had more. Okay, now, on his 26th birthday, Matthew started an annuity for his retirement. He deposits $630 each month into an account, earning 4% annual interest compounding money. He determines that he will be able to retire once he has $1 million in his retirement account. Determine how old Matthew will be when he retires. Well, notice that Matthew is starting all this stuff when he is 25. So his starting age is 25. Let's put 25 down here in our notes. All right. And I'm pretty sure that we're going to be using the exact same interactive figure. Yeah, exact same one. Probably wasting my time doing that. So let's wait for that to come back up. And notice that our investment goal is $1 million. So we want to change this to $1 million. That's 1 followed by 6 zeros. 1, 1, 2, 3, 4, 5, 6. Which actually is not going to be enough. He has an account that earns 4%. And that's a deal breaker too. That's not that much money. That's not that much. It is compounded monthly. There we go. And he is going to deposit $630 every single month into that account. Okay, well there we go. Well, it looks like 25 years is not going to work. Let's add a few more years to that. Let's try 35. Nope, not quite there yet. Let's bring this to 45. Actually, let's bring this to 60 years. Okay, it turns out that he will reach his goal in 46.05 years. Okay. So he's going to be 25 plus 46.05 years. And we're going to round to the nearest year. So that's going to be 25, 46.05. That is going to be 71.05 years. He should be 71 years old when he actually gets there. Because notice, it's going to take him 46 years after his first deposit. His first deposit is on his 25th birthday. So he will be 25 plus 46 years old. There you go. In that case, we are done. And that is pretty much, no, that is exactly how you do those particular problems. So you can, once you're done, you can save your work. And shocking as it might be, got them all right. Awesome. That is everything I have to cover section 3.3b. If you have any questions, please feel free to contact me. And this is Bob Boyle, signing off.